different. How can they be different? Well, for example, let me give you a couple of empirical formulas of things you know. What's the empirical formula for carbon dioxide? Okay, CO2. You cannot break that down into a smaller ratio. 1 to 2 is the smallest ratio that you can come up with. Okay. Salt. What's the formula for salt? NaCl. Its ratio is 1 to 1 ratio. For every 1 sodium, you get 1 mole of chlorines. So that's the simplest ratio. Let me ask you if this is the simplest ratio for this compound. This is the one you actually found percent by mass of. So can I simplify that down any more? I have 3 calciums, 2 phosphorus, and 8 oxygens. Can I simplify that down more? No. I cannot simplify that down more. So these are all considered molecular formulas, and empirical formulas are exactly the same. But, for example, if I have glucose, something that you guys talk about in biology, glucose formula is C6H12O6. So that is the molecular formula for glucose. That's actually how it goes in together. It's a cyclic structure where you have carbons. I'm giving you more information you need, but that's okay. You got carbons in a cyclic structure, and then you've got hydrogens off of there. And then you got OHs off of there too. And it goes around and links. And you guys will start putting these Lewis structures and that together later on next semester.
Great.
Yeah, they're fun. So, what is the empirical formula for this? It's not going to be the same as the molecular, right? So what's the simpler ratio? All of them can be divisible by what? 6. So C6 becomes C, H12 becomes H2, and oxygen becomes O. Okay, now, when we calculate the empirical formula, when we find the empirical formula, it doesn't necessarily transfer that's the actual formula of the compound. It's the simplest ratio. So if I give you percentages for glucose, and I give you percent carbon, hydrogen, and oxygen, and then we'll go through steps to show how you would find the mole ratio. We would always come up with this ratio, CH2O. We never come up with a more complex ratio when we do these calculations. Now there's a way, which we'll talk about later, how you can come up with the molecular ratio, but you need some more information to be able to do that calculation. So all we're concerned with is empirical formula. Another one is hydrogen peroxide. So hydrogen peroxide is used for a variety of different things. Some things as a disinfectant. It can be used as a bleach, for example. Yeah, they put it in toothpaste to whiten your teeth. Okay? So, or peroxides. So H2O2 is the molecular formula. What's its empirical formula? H-O. Okay? So that's the empirical formula for hydrogen peroxide. So we'll come back to molecular formula later on. So what I'm going to initially start out doing is giving you some weights of elements that make up this compound, and then from those weights we're going to determine the actual formula. So you guys write that down. As you guys are writing that down, on Thursday you guys get the opportunity to do a lab that will take magnesium and heat it up to over 1,000 degrees to get it really, really hot for a specific period of time in which to do a reaction with gases from the air. You're going to react it, and then you're going to reweigh it a couple times And then by doing that, you're going to be able to come up with a formula for the magnesium and an element in the air that reacts with it. And you're going to go through this process of experimentally taking data like it's up here and then going ahead and using that in which to find a formula for it. So a formula, all it is a mole ratio. That's all it is. It's saying that CO2, you have 1 carbon for every 2 oxygens. That's all it's saying. And you guys remember what theory states something about ratios and how things go together? Yeah. So Dalton said these atoms, when they get together to form compounds, they're always going to get together in a whole ratio. We have to have whole atoms that go together. It could be a 1 to 2 ratio, 1 to 3, 2 to 3, whatever that ratio is. So now that we can count atoms by knowing their weights, now we can find out a formula. So this is what I'd like you to do. I'd like you to go ahead and find the moles of aluminum from the 2.21 grams of aluminum. And I'd like you to find the moles of bromine. So what we're doing those problems. Remember, we're doing problems to apply here, and we're just going to find moles of aluminum and then moles of bromine, and then we're going to compare them. Because if we know moles of both of them, then we can get the ratio. And it should come out to be a whole number ratio eventually. Because that's what Dalton's atomic theory said, is when these go together, they go together in a specific mole ratio. So go ahead and find the moles of aluminum and moles of bromine. Shouldn't take you too long. So when you take and divide them out, you get your mole ratio. Now, at this point in time, we've got to get them in the whole numbers. And this trick, some students forget to do this, so they forget, they're doing problems, they get the empirical formula, they go, oh yeah, you told me I needed to find moles, and they get to this point, and they don't know what to do here. They're like, I'm lost. What do? I don't know. I know that there's more bromine than aluminum. So I'm going to have at least one aluminum with multiple bromines. But I don't know how to get that. And then you go, oh yeah, I remember now. You take and divide by the smallest number of moles in any of your calculated values that you have. Here we have 2 calculated values, aluminum and bromine. So I'm going to take both of them and divide them by the smallest number of moles. Because what that does, it gives me a ratio that can give me some whole numbers, I'm hoping. So this one definitely is a ratio that's a mole number is 1. So anytime you take its number, divide it itself, you get 1 of it. So then you take this here and divide it in, you get a number that's 2.99. So when I divide that, I get 2.99. So do you think that's close enough to 3 that I can make that 3 moles of bromine? Yeah. Yes. If you got a number like 2.98, 2.97, 3.02, that we can round down and round that up, then that's what we'll do on that one. And so what's the formula for this? AL, we don't need to write a 1 with AL because AL symbol stands for 1. And then BR, what? 3. Everybody see why? See, the ratio they say, based on these masses, are you get 1 aluminum for every 3 bromines. And if that's the case, then I write the formula with a subscript for 3 for bromine. So it's AlBr3. And so this is going to be your subscripts. If you get a number greater than 1, that'll be your subscript. Don't put AlBr 2.99. Okay? It's 3. It's got to be a whole number. Okay? We're going to do one more. The next one we do is based upon percentages. Okay? So these are actually, this is an experiment that's been done. They do the work, they do measurements, and they come out with these different values. Like in AP Chemistry, what we did is I gave them a compound of copper chloride with some water hydrate. They call it a water hydrate. And so they had to figure out copper and chlorine and then they had to figure out how much water was present in moles of each one of those. And so they went through and did that, and then they had to figure out the formula based upon that. We'll do something similar to that, but we won't have water in it. We'll have just two elements that we're working with. Okay? If you want to write that down, that's the next problem we're going to do. Hello? Yes, I do. Uh-huh. Dylan, you need to go down. So again, on this one, you're going to take the percentages that you're given, and these percentages you get from either experiment or in theory when you take a look, is how these percentages come about. And you just change the sign of percent to grams, and then you just change grams to moles for each one separately, so that you can get a mole comparison. So again, just go ahead and find the moles of each one of these. So again, your formula is AgNO3 because we come up with 0.588, 0.586, 1.77. We divide by the smallest, we get the ratios 1:1:3. And then so the formula would be AgNO3. And then the assignment is on the board. Page 212, 44 BC, 44 C, or 46 CE.